Dislocation modeling of tectonic landforms in Mare Frigoris. And the talk will be given by Nathan Williams. Go ahead.
Right, thank you.
Thank you.
Just wait. All right, well, thank you and good afternoon. My name is Nathan Williams, and I'm going to be talking about my recent attempts at doing fault dislocation modeling of different tectonic landforms in Mare Frigoris. So I'd first like to acknowledge and thank my co-authors who really made this possible, as well as the whole LROC team, because their fantastic data products really make this possible, as we actually have some constraints for these models. So I'll start out talking a little bit as a summary of Mare tectonism as a whole. I'll go into specifically the area that I'm focusing on, Mare Frigoris, then discuss a little bit about how exactly I'm going to be doing these models of the topography and the relief of these features. Talk about some of the preliminary results that are hot off the presses, and then conclude and add in some future work that I hope to do. So in the near side basins, Mare tectonism has been active for most of the lunar history. The extension ended about 3.6 billion years ago when the moon shifted from a state of net expansion to contraction. However, the contraction itself in the basin seems to have continued until about 1.2 billion years. However, that's continued perhaps a little more recently on a global scale due to thermal contraction of the whole moon, but that has been a relatively secondary effect. However, the contraction in the Mare basins is primarily accommodated by the sinuous wrinkle ridges, which I've shown here on your right. These sinuous wrinkle ridges are interpreted to be folded basalt layers that overlie thrust faults that are compressible structures that may extend down to some depths of maybe a couple kilometers. Now, in some of the Mare basins, these wrinkle ridges have preferred orientations that are either radial to or concentric with the centers of those basins. And this is typically associated with basins that have mass cons or mass concentrations. We have excess mass that then applies a load to the basin and subsides the crust underneath. And that substance can cause flexural bending, and the compression actually causes these features. However, not all the Mare basins have these mass cons, yet they still have wrinkle ridges. So this leaves the obvious question, why are they there? And so the origin of the compressional stresses that form wrinkle ridges in non-mass con environments really remains an outstanding question to this day. So one way to address this is to look at the wrinkle ridges in areas where we don't have very large mass cons. And one great example of an area is Mare Frigoris. So I've shown up here a tectonic map that we have made of Mare Frigoris. It's on the northern near side of the moon. Essentially, if you look at the man on the moon, Mare Frigoris would essentially be the unibrow. It's a very elongated basin that is over Mare Imbrium and its Serenitatis. It does not really clearly associate with a single impact structure, and its origin is also somewhat enigmatic. But because of its high latitude, or mid-latitude, about 60 degrees north, it provides us with good enough spatial coverage with the LROC overlapping passes, so we can get great image coverage, as well as having really excellent lighting conditions, so you actually really see the morphology as opposed to more nadir sun angles. In addition, as seen in the next figure, this is the Grail gravity map from Ria Zuber and the Grail team. This is 3-year anomaly. The western part of the basin doesn't have a very strong gravity anomaly, which we'd expect for some of the other basins like Mare Imbrium at the bottom of the map. And yet, as you can see in the western part of the basin, where those red lines are, those are a lot of wrinkle ridges that occur there in the absence of that large mass con. So to address this, we have decided to apply fault dislocation modeling, which is basically one method that we can use to try to understand what's actually going on beneath the surface. So key step to better understanding the occurrence of these wrinkle ridges in the Mare basins, especially in the non-Mare cases, is understanding the behavior of the underlying faults that are at depth and we can't directly see unless we were to go back and actually dig a giant trench. But the surface deformation of these faults in a half space allows us to actually look at this by looking at the topography, because we can explain the surface relief as a function of several nonlinear equations defined by Okada. So we apply these equations in a fault dislocation model to basically estimate the geometries and the displacements for the faults that underlie these wrinkle ridges to try to constrain those parameters. And in order to do that, that's when LROC comes in with their incredible high-resolution topography at 2 to 5 meter scale, so that we can constrain that predicted relief. So to specifically apply this, you can either do this with a manual method, which I have done for single planar faults that will take up to 2 weeks for a single run, or you can apply a much better method of optimizing. One such way is using a genetic algorithm. In this case, you can solve for multiple variables in nonlinear systems simultaneously, and as well as get quantitative error estimates for those at the same time. So with the genetic algorithm, as opposed to some other approaches, you first define the deformation error functions that you want to optimize. You define the variables as well and select those parameter ranges that you expect the faults to constrain with. Then you generate initial small population of expected deformation patterns based on the Okada models. So you calculate those deformations, and based on the errors of those, when you minimize those runs with the least errors, you select that little subset and you essentially mate those together, sort of like with chromosomes in the cells. So you mate those together to create a new population of the same size. You randomly mutate a little bit so you don't get focused on a local minimum and miss the global picture. And then you have to iterate over many times in order to actually get a robust solution. So applying that genetic algorithm general approach to the fault model, we're solving for locations of the fault, their size, their depths, the displacement and slip on the faults, as well as the orientation, their strike and the dip angle that goes down. So we solved for the fault planes. We gave it a certain number of fault planes. We could vary that, but 3 to 5 tended to work pretty well. These models will show in a minute. We solved for 5. And these were all going down from the surface from a single point, but with decreasing depths as you go down, or decreasing dip angles as you go down with depth. So it's curving back towards the surface a little bit, but doesn't actually come up. So it's a curved fault geometry that we're solving for. But we do allow to have a planar fault as well, which would be even simpler. So we do this for 1,000 of these genetic algorithm generations, and we run the entire thing over 100 times again to come up with some sort of an empirical estimate for what the errors on these models are. So this is the area that I specifically focused on. This is a wrinkle ridge in western Mare Frigoris. These images are from the LROC NAC digital terrain model. And I've selected the area that's in the white box, blown up on the right side, that has a relatively linear section of the wrinkle ridge. Eventually we will extend to the more sinuous geometry, but for this one section, we can focus on that at the moment. When we do solve for the displacement, we get the figure on the right here, and this is the median solution after all these runs. And it does very well approach the high relief that's on the immediate ridge, as well as the broader arch that's kind of in the orange colors. Look back to it there. So this does fairly well match the deformation that we do see. In order to get this displacement field, we had to input several of these. These are the input parameters that worked best for it. So we start out with a series of dip angles. Dip angles that tended to be greater than 45 degrees or less than 30 degrees gave us lengths that were essentially 0. So those segments of the fault don't really exist. However, between the range of about 45 and 30 degrees, that's where the solutions actually lay. And so the actual numbers up here, but essentially the take-home message is that these faults are going down to depths of about 2 kilometers based on these models. And that could still be towards the bottom of the Mare fill here or within it, which is as we'd expect. But the important part is that these faults do actually appear to be contained within the Mare fill as opposed to being more deeply buried or more deeply sourced. So in conclusion, these inverse methods really allow for simultaneous computation of these multiple fault parameters to find optimal solutions without having to spend weeks or months trying to find a single fault plane, as I have done in the past. And the preliminary results showed that these wrinkle ridges do occur shallowly within the upper 2 kilometers as we would expect, and are probably not likely sourced much more deeply into the North Pacific crust, and perhaps due to some other process not related to the Mare Basin itself. But in future work, we'd like to extend this to change it up. Instead of having rectangular fault planes that don't really work well with the sinuous geometry of the fault, we can instead use triangular faults, little fault patches, that can more easily mesh around the surfaces. We also like to expand to models that include more spatially variable slip and displacement on the faults. We kept it uniform, but realistically on Earth, we know that's not the case. It's a more variable distribution. So we can add that complexity as well. We also like to, once we have those models at least, we can start to invert those for what we expect the exact stresses and strains to be in those areas. And that can constrain not only the stress that we would expect in the past, billions of years ago when some of those faults were active, but a few of them may have also been recently active as well, as evidenced by very small scale, meter scale troughs that occur in the back limbs of these, which indicate that they're probably on the order of tens of millions of years old at the most, because otherwise they'd infill. So we may be able to get a more recent stress estimate for the lunar crust and the Mare basins this way. And finally, we also like to apply this method to wrinkle ridges elsewhere on the moon, in addition to just Mare Frigoris, because Mare Frigoris is just one case where we do see these features, and the implications go much more broadly. So thank you. Again, I'd like to appreciate my co-authors and the LR team for their great help with this, and I'd be happy to take any questions.
Thank you very much. We have time for questions.
Riz Uber from MIT. Yeah, nice talk. Is there any spatial pattern associated with these that could give you some insight into the possible stress source?
The
spatial pattern.
Spatial distribution of the surface trace, you mean?
Right. Yeah. These seem to be a different population than
yeah, and
most people have been mapping.
I can scroll back here enough. Yes, this is going to take a while. The series of ridges, wrinkle ridges in western Mare Frigoris appear to be subparallel to each other over very long length scales. I'm not sure if it shows it very well on this screen. There is a, look here for gravity anomaly. There is a positive gravity anomaly right here, but it doesn't extend very far north. But there are these parallel series of wrinkle ridge segments along here that do not fit with any basin, radial, or concentric pattern like we expect for a mascon. Right. So we may have to invoke some other means to form them.
Well, because if they're just due to cooling stresses, say, then you wouldn't expect to see a spatial pattern. So there's information in that.
Yes, there is. And it's still unresolved mystery as to why it shows that exact pattern, but there is something there. And that may be resolving some sort of other structure. Yeah, thanks. Other questions?
I actually have one. What does the...
I've got my mic.
What about the Grail crustal porosity constraints that we have now? Do those play any role or any factor in your modeling?
Probably not for this case, because these, at least right in here, these are dealing in the Mare basalts, which have relatively low porosities. That shouldn't play a factor. When we do get to the stress and strain inversions, that will play a small factor. I think that is mostly the case for dealing with the highland features where you have rare porosities. So I'll be dealing with a different class of tectonic commercial landforms called low-base scarps. And yeah, there you definitely have to take that into account. Yeah. Yep.
Thanks a lot.